Motion on a plane with constant acceleration. We have studied in the previous lesson, that is motion along a straight line, about a body moving with constant acceleration. In the same way, we are going to study the motion of a body moving with constant acceleration in a plane. Let the velocity of the object be v naught bar at time t equal to 0 and v bar at a time t. Now here v naught represents initial velocity and v bar represents final velocity. Then how can we write acceleration? Acceleration a bar is nothing but change in velocity by time. What is the change in velocity here? V bar minus v naught bar by t minus 0. So that is nothing but v bar minus v naught bar by t. Now if you are going to cross multiply and rearrange, you are going to have the expression as v bar is equal to v naught bar plus a bar into t. This is nothing but your first equation of motion. Now here if you see, this is a velocity of an object in a plane. Plane means xy coordinate system will be there. So any vector will have how many components? Two components. That means v bar will have two components, v naught bar will have two components, a bar will also have two components. Let us see. In terms of components, Vx is equal to v naught x plus ax into t. This is along x-axis. That means the entire equation is resolved into how many components? Two components. One along x-axis, another one along y-axis. Where time is a scalar which don't have any component, it remains the same along x as well as y. And Vy is equal to v naught y plus ay into t. Now this is the y component of this equation. That means v bar can be represented as vx I cap plus vy j cap. V naught bar can be represented as v naught x I cap plus v naught y j cap, and a bar can be represented as ax I cap plus ay j cap. Let the position vector of the object be r naught bar at a time t equal to 0 and r bar at a time t. Then the displacement is the product of average velocity and time interval. Therefore, r bar minus r naught bar, which is nothing but change in position. We have seen in triangle of vectors also, and even in displacement vector also, change in position is nothing but displacement vector, which is equal to average velocity. Here how many velocities we have? One initial velocity, another one final velocity. So what is the average? V bar plus v naught bar by 2 into t, because your time remains the same. So displacement is nothing but average velocity times time, equal to, now v bar can be represented as v naught bar plus a bar t plus v naught bar by 2 into t. Now you're going to add these two. You're going to have the equation as r bar minus r naught bar equal to v naught bar t plus half a bar t square, which is your second equation of motion. That is s equal to ut plus half at square. Now here this r minus r naught is nothing but s bar. Change in position is nothing but displacement. Now r bar can be written as r naught bar plus v naught bar t plus half a bar t square only. Now here this is also the equation in a plane. That means again this equation will also have how many components? Two components. One along x-axis, another one along y-axis. So in terms of components, when you write this equation, so the x component is nothing but x equal to x naught plus v naught xt plus half axt square. That means r bar x component is x, r naught bar x component is x naught, v naught bar x component is v naught x, and a bar x component is ax. Similarly, along y-axis, you can write the same equation, that is the y component of this vector as y equal to y naught plus v naught by t plus half ay t square. So this is how you are going to resolve the vector in a plane into how many components? Two components, one along x-axis, another one along y-axis. Relative velocity by vector algebra. Already we have studied about relative velocity in motion in a straight line, but here we are going to represent and study the same by using vector algebra. When the velocity of an object is measured with respect to an object which is at rest or in motion, the velocity measured is known as relative velocity. So relative velocity is nothing but always we have to compare the velocity of an object with respect to another object. Consider two objects A and B moving with velocities VA bar and VB bar respectively. Now that is a VA bar vector and that is VB bar vector which is taken in space. To find the relative velocity of the object, say A with respect to the object B, the velocity minus V bar is superimposed on the object B so as to bring it to rest. That means I am going to take the negative vector of VB bar. So this is VB bar and this becomes minus VB bar. To nullify this effect, velocity minus VB bar is superimposed on the object A also. I am going to imagine the parallel vector of minus VB bar at the terminal point of VA bar. Now if you are going to use triangle law of vectors, the resultant of VA and minus VB bar gives the relative velocity of VAB of the object A with respect to the object B. That is OPR. OP represents VA bar, PR represents minus VB bar. Now OR represents the relative velocity, that is nothing but VAB bar equal to VA bar minus VB bar. Mathematically, VAB bar is equal to VA bar plus of minus VB bar because we are taking opposite of it, that is a negative vector of VB bar, or VAB bar is equal to VA bar minus VB bar. Magnitude and the direction of the relative velocity in terms of magnitudes and angle theta between them. Let's suppose I am going to consider the velocity of the first object VA bar. Let OA represents VA bar. That is the second object velocity, that is VB bar. I am going to consider the negative vector of VB bar, that is minus VB bar, at the initial point of VA bar. That means both are separated by an angle theta with respect to one another. So if this is theta, this becomes 180 minus theta, because if you take a straight line, the angle at a point in a straight line is 180 degree. So if this is theta, that becomes 180 minus theta. Now imagine a parallelogram over here. That means the parallel side of OA is imagined at the terminal point of VB bar. In the same way, imagine the parallel vector of VB minus VB bar at the terminal point of VA. So we are going to have a parallelogram here. Let OR represents the resultant of both VAB bar. Now alpha represents the direction of the resultant VAB bar. Now use the parallelogram law of vectors. VAB bar is equal to VA bar minus VB bar. The magnitude of the vector VAB bar is, use parallelogram law of vectors, you are going to get the formula. VAB equal to root over VA square plus VB square plus 2 VA VB cos of 180 minus theta. Cos 180 minus theta is nothing but 180 minus theta means second quadrant. So cos of 180 minus theta is nothing but minus cos theta alone. So you are going to have this expression VA square plus VB square minus 2 VA VB cos theta. The direction of the vector VAB bar is tan alpha is equal to B sin theta by A minus B cos theta. This is the formula for us. Now here A is nothing but VA, B is nothing but VB. When two objects are moving along the same straight line, so VAB is equal to VA minus VB if they move in the same direction. VAB is equal to VA plus VB if they move in the opposite direction. When they move in opposite direction, we have to take the opposite of VB bar.